Today we're just going to start conservation of energy. We're not going to finish this because it's actually a pretty big concept, but I'm going to teach you one really important thing about conservation of energy. And what is conservation of energy though? Let's talk about that. So basically it means that the energy that you put in is equal to the energy that comes out. So when you put in the energy of like biking up a hill here, and then you're at the top of the hill, you've gained all this potential energy, right? And what did it take to gain that potential energy? A bunch of kinetic energy. And then you're up at the top of the hill, and what's it like to go down? If you don't brake, what's going to happen? You just coast right down, and so all that energy you put in to get to the top of the hill just comes out when you go to the bottom of the hill. And then all this potential energy just converts itself to kinetic energy. Okay? It's the same thing with this thing called a pendulum down here, right? So if I have this pendulum, so here's a string, and we call this a bob because it bobs. So we're going to call that bob. Anyways, the bob, when it's at its fullest height, it has a bunch of potential energy, right? We just gave it a bunch of potential energy. And as soon as you let it go, it's not like the energy just disappears. What happens to it? It's converted all over here into kinetic energy. Okay? When it's at its lowest point, and then it converts itself back into potential energy once it gets to its highest height again. So that's what's happening is we have this conservation of energy. Energy isn't being created or destroyed. It's just being transferred from one form to another, okay? So this is a law of conservation of energy when we're talking about potential energy and kinetic energy, okay? So today we're just going to talk about their maximums, right? When we have like the highest point in something or the lowest point which has its maximum kinetic energy, okay? So we know if we talk about the law of conservation of energy, then energy shouldn't be created or destroyed. So something's maximum potential energy should equal to its maximum kinetic energy, right? So here with the pendulum, here is its maximum potential at its highest height, and then it goes down, and once it's at its lowest height and it can't swing further down anymore, then all that potential energy is gone because it's doesn't have any more potential to fall down because it has this string keeping it right here. Okay? Same thing here. If the biker's at the very, very bottom and then puts in all this work to get to the very top of the hill, then that height is giving that biker a ton of potential energy. So that would be its maximum potential energy. But then what happens? They go down the hill. And then at this point, once they're at the bottom of the hill, all that potential energy has been converted into kinetic energy. And that is when they are at their maximum kinetic energy. Okay? So since there's a conservation of energy, we know maximum potential energy should equal to maximum kinetic energy, which is really, really nice. Okay? So here we go. Maximum potential is equal to maximum kinetic. This doesn't always happen, okay? But we are just working in a perfect world in physics because, well, why not? Sometimes we just need a perfect world to live in, okay? Or at least just to dream about. So in our perfect world, there's no energy lost to friction or heat or anything like that. It's just all nicely conserved, okay? So no such thing as air resistance here. So that's what I need you to know. When we have our maximum potential energy, it's equal to the maximum kinetic energy. But this whole maximum thing is so, so important, okay? Because potential energy isn't equal to kinetic energy at any point. It's just when they're at their maximums, right? Because it's saying all the potential energy here is completely being converted to kinetic energy at the bottom of the hill. So, so, so important that you understand that, okay? So that's what we're going to consider is that basically potential energy at the highest point, because that's what gives something gravitational potential energy, is being really, really high up, is equal to the kinetic energy at the lowest point. Okay, so that's really, really important. So we're considering the fact that when potential energy is at its highest and there's no kinetic energy, it transfers itself all to kinetic energy when it loses that height because it's losing that gravitational potential energy. So let's do just a couple examples of this and maximum kinetic or potential energy turning itself into maximum kinetic. And let's just get that kind of viewpoint and that concept down before we move on in conservation of energy, because it can get a lot more complicated. So here we have a pendulum bob with a mass of 0.40 grams, kilograms. Let's write that down. And it's lifted up 30 centimeters, so that's its height. Oh, usually we don't like things in centimeters, do we? So we should probably convert that to meters. Remember, there's 100 meters in a centimeter, so I'm just going to divide that by 100. So my height should actually be 0.30 meters. Careful with the centimeters. Remember, there's only 100 centimeters in a meter. A lot of people want to divide that by 1,000. I've seen it a lot. Okay, so I just want to know how much potential energy it was given. Well, remember, potential energy, gravitational potential energy, is equal to mgh, mass times g times the height. And remember, g is just a constant. Perfect, nice and easy. We can calculate this no problem. Mass is 0.4 kilograms. G is always 9.81 meters per second squared. And h is 0.30 meters. Okay, let's calculate that. Okay, and that gets us 1 point. Well, I need two significant digits because 0.40 has 2 and 30 has 2. So that's 1.2 joules. Okay, so that is the potential energy that was given to this pendulum. Okay? If that's the potential energy given to the pendulum, that's its potential energy up here at the very highest height. Okay? So right here, the very highest height, that's its maximum potential energy. So that potential energy there was 1.2 joules. So I want to know, what's the pendulum's kinetic energy at the bottom of its swing? Well, at the bottom of its swing, what's happening? It's at its maximum kinetic energy. Remember, when we have our maximum potential energy, it should all be converted to your maximum kinetic energy as it falls down. So therefore, it should just be the same as your maximum potential, because here, all potential energy has converted to kinetic energy. That's what we know about their maximums. So we know that kinetic energy is equal to 1.2 joules at the bottom of the swing, because that's its maximum potential energy. So again, here, if at the top of the swing it's 1.2 joules, then at the bottom of the swing here has to be also 1.2 joules. Okay? So that is something that's really, really important to know. So I want to know, what is the speed of the 0.40 kilogram bob at the bottom of the swing? Okay, I want to know the speed. I have the mass. What's something we know with speed and mass? Oh, probably kinetic energy, because it looks like we also have the kinetic energy, right? So that's the nice thing about this, is that we can use the potential energy that we originally had. Since we know it all converted itself to kinetic energy, now I can go to the kinetic energy formula, which is 1/2 mv squared. And that is all converted to kinetic energy. So we know kinetic energy here is actually 1.2 joules. And then we also have our mass, which is 0.40 kilograms. And therefore, we can find our velocity. Okay, so you're going to get used to this a lot. Don't you worry about it. At first, it's kind of like, huh? What are you doing? Why? Why are you doing this? But remember, we calculated our potential energy. It was 1.2 joules. And that was the maximum potential energy because, of course, that is when it was lifted up to its highest height. Okay? And so therefore that 1.2 joules has now completely converted itself into kinetic energy. And now we need to go ahead and solve for velocity. Okay, so let's do that. So we know our kinetic energy is 1.2. Just a little note here, the answer was actually 1.1772 for this potential energy. So that's actually what I'm going to use when I calculate all this, okay? So that's equal to 1/2 times 0.40 kilograms times the velocity squared. Okay, so let's multiply that 1/2 times 0.04 first. So, or 0.40, so that's 0.20 now. I'm going to ignore units for a minute, which feels so wrong, but again, I know it helps you guys. Okay, I want to figure out velocity. So right now I'm multiplying by 0.20, so I have to do the opposite, and I need to divide. Okay, so I'm going to divide both sides. That gets rid of that there. Okay, 1.2 divided by 0.2 gives me 6. But remember, that's equal to the velocity squared. That's not actually equal to the velocity. So now, in order to get the velocity, I need to, anybody remember? I gotta square root both sides, because that's what's going to get rid of that squared on the v. The opposite of squaring is square rooting, right? Okay, so let's do that. And what do we get for our velocity? We get 2 point, what, how many significant digits do we need again? We need 2, we have 2 there, and our previous things we had 2 as well. So that is actually going to be 2.4 meters per second. Please, please, please do not forget your units at the very end, okay? Just for the sake of solving right now in Science 10, I'm going to say it's okay if you leave the units out of the calculation part, but you have to have units on your final answer. Okay? So there we go. That is how we can take the fact that maximum potential energy turns itself into the maximum kinetic energy to solve for something with kinetic energy that we didn't have. Okay? Let's try a few more of these. So now we have a roller coaster and its passengers, and it has a combined mass of 1,000 kilograms. Okay. So the roller coaster starts from rest at the top of the biggest dip. So remember, you have a roller coaster and it's going to like go like that. So they're at the top here. Cute little roller coaster car. You know, people, they're there with their hands up. They're ready to go down this roller coaster. Okay, so starting from rest at the top of the biggest dip, it's 90 meters tall. So that's our height right there. Okay, so we want to know what's their speed at the bottom of the roller coaster. So they're going to go all the way down here, and I want to know what's the speed down there. Okay, what? Mass, height? That has nothing to do with speed. What's going on? Oh, well, of course, at the top of the roller coaster, what do they have? They have a maximum potential energy, right? Because it's the highest they're going. And then once they get to the bottom of the roller coaster, guess what? We have the maximum kinetic energy. And so therefore we know that the maximum potential energy should equal to the maximum kinetic. So if we calculate potential energy at the very top, that'll be the same as the kinetic energy at the very bottom. So let's start with that and calculating the maximum potential energy at the very top of the roller coaster. So remember, potential energy is mgh, okay? So my mass is 1,000 kilograms. G is always 9.81 meters per second squared. And my height is 90 meters. Okay, that gives us a maximum potential energy of, are you guys ready for this? Oh my goodness. 882,000 900 joules. Now, if this was our final answer, I would definitely have to round this and put this in scientific notation. The thing is, it's not our final answer, okay? So I need to find their speed at the bottom. So what's the next thing I have to do? Well, remember, this is our maximum potential energy. So what else is it equal to? Our maximum kinetic energy. Okay, so there we go. So we can kind of do a whole other part of this now, where now I'm using this 882,900 joules as my maximum kinetic energy. Okay, because then I can go over to my kinetic energy formula, which I know is equal to 1/2 mv squared. And hey, we already did one where we basically did this, okay? I'm just doing it all in one now instead of asking you in pieces, okay? Because we know our kinetic energy at the bottom is equal to the potential energy at the top. So that's 882,900 should equal to 1/2 times, what's the mass again? That is 1,000 kilograms. Times velocity squared. And then we are going to solve for velocity. I'm going to do it exactly the same as I just did. And I'm not going to explain it this time. I'm just going to show the steps. Okay? Okay, and so we do all that. We get a final answer of 42 meters per second. We do need two significant digits because we got the 90 meters from the original thing here. So that is my final answer, is 42 meters per second, okay? So there we go. Anytime you have that, you know, it's at the highest height and then goes to the lowest height, we have all our potential energy converting into kinetic energy. So we have our maximum EP is equal to our maximum EK, okay? And it's like that anytime you hear something that's going from the highest height to the lowest height, okay? That is how we would solve for something for velocity. But let's switch this around again, where maybe we can have the maximum kinetic energy and then need to find something that has to do with potential energy. So we have an 80 kilogram biker. Oh, that just gave us mass, so we should probably list that. It starts at the top of a hill and rides down. If they didn't apply the brake down the hill and their speed at the bottom of the hill is 9 meters per second. Oh, okay, stop. 9.0 meters per second. How high is the hill? So again, we have something going from the very top to the very bottom. Okay, so we know that our biker here is going down this hill, and again, at the top we have maximum potential energy, and at the bottom we have maximum kinetic energy. Okay, so we know all potential energy is being converted to kinetic energy. But in this case, I want to know how high this goes up. So I need to know the height here, right? So in the last one, we wanted to know the velocity at the bottom of the hill, but it gives us that. So now we need to know the height. So this is basically working backwards, because now I have the ability to find out the maximum kinetic energy, and I need to then go backwards and find the maximum potential energy and find the height of the hill, okay? So basically just start with which one you have the most information for. If you're ever in doubt, look at both of your equations, right? EP is equal to mgh, EK is equal to 1/2 mv squared. Look at that and say, what do I have? I have mass and velocity, so obviously I have to use kinetic energy because this has nothing to do with velocity and has a height, and I don't have the height, so I can't use it, right? Sometimes you guys are just so used to being confused with math and variables that you just think, oh, well, I obviously can't do anything because I'm supposed to be confused. It's supposed to work and it's not working for me. No, sometimes the fact that it's not working is actually just telling you that you are on the right track, that you can't use that MGH right now because you don't have height, right? So in this case, we can find the maximum kinetic energy and then apply that to my maximum potential, okay? So remember that's equal to 1/2 mv squared. So that's 1/2 times my mass is 80 kilograms and my velocity is 9.0 meters per second. I'm going to square that, okay? So for my kinetic energy, again, that's just 1/2. We'll put that as 0.5 in the calculator, times 80 times 9 squared. And when we do that, we get 3,240 joules of energy. So that is your maximum kinetic energy. But what else do we know? We know that's also equal to our maximum potential energy. Okay, so now we can go over to the potential energy formula because we know that maximum potential energy is equal to maximum kinetic energy, which here is 3,240. Okay, so let's do that. So my potential energy now, I know is equal to mass times gravitational acceleration times height. I need to solve for height. Okay, in this one, I'm going to show you how to rearrange just because this one's so much nicer and easier to rearrange. And that's just dividing by mg on each side. Okay, so that's all I got to do there. And then I get the fact that height is equal to potential energy over mass times gravitational acceleration. So my potential energy is 3,240 joules. And I divide that by my mass, which is 80 kilograms. And 9.81. Okay, so I'm going to do that. Remember to put 80 times 9.81 in brackets. And when you do so, you should get 4.1 meters. And yeah, it is definitely still two significant digits. We have 9.0 there, which is 2, and 80 there, which is 2. Okay, so that's what you got to know. Maximum potential energy is equal to maximum kinetic energy. And at this point right now, we're just going to talk about gravitational potential. So just remember the potential energy when it's at its maximum, which is when it's at its highest point, right? So that could be the top of a hill or the top of a pendulum swing. Or if I'm dropping something, it's the height I dropped it from. Or if you're jumping off the diving board, it's the height of the diving board, right? That is your maximum potential energy or where that's happening. And then your maximum kinetic is always when it's at the bottom, okay? And so that's just what you need to know. The energy at the highest height is its maximum maximum potential, and at the lowest height is maximum kinetic, okay? And those two things are equal for it, but it only works for the maximums, okay? It only works for when you're at the highest height and lowest height, when all potential energy has been completely converted to kinetic energy. Because at the bottom of the hill or at the bottom of the pendulum swing, there's no more potential energy left, okay? It's all been converted to kinetic energy. And that's what we need to know, okay? Well, there you go, you guys. That is the beginning of a conservation of energy. There's definitely a lot more to go over, but I'm going to leave that for next week. I hope you guys have a really great rest of your day, and I will be talking to you later.